Hello students, in today's video presentation we'll be covering the Maxwell's reciprocal theorem. It's a very straightforward theorem based upon the law of conservation of energy. We'll just first go through the statement. The statement goes like this. It states that deflection at any point in a system due to a unit load acting at any other point of the same system is equal to the deflection at the second point due to a unit load acting at the first point. So here in the figure we have two locations on this beam. It could be a beam, a cantilever, or any other kind of a complex system also. We have two locations here, I and J, and we have the forces Fi, which is acting at location I, and Fj, which is acting at location J. So the theorem can be mathematically put in this form, that is Aij is equal to Aji. Here Aij is the influence coefficient, which means that it is the deflection at location I due to the unit load acting at location J, and likewise Aji means this is the deflection at location J here due to a unit load acting at location I. So now we'll go through the proof of this theorem. I'll see it's going to be very straightforward. So we have this system, and here in this beam, if we know the stiffness, or in other words, if we know the section modulus and length of the beam and the material properties, and we also know the magnitudes of the forces at Fi and Fj along with their locations, that is the locations of point I and point J on the beam, we can determine the deflection curve for this beam. And once we know the deflection curve, we can also determine the strain energy which is stored in the beam. That strain energy actually results from the work done by these forces Fi and Fj on the beam material. Now this deflection curve of the beam is independent of the order in which these forces Fi and Fj were applied. So if you are to solve a problem concerning the deflection of this beam under the influence of these forces Fi and Fj, you don't have to worry about, you don't have to think about whether Fi or Fj were applied simultaneously or whether one of them or either one of them was applied before the other one. So based on this understanding, we go ahead with the proof. So here we have the first loading scheme where we gradually apply the force Fi at location I here, right? So this work done by this force Fi is the average force starting from 0 to the final magnitude Fi multiplied by the net displacement. So the net displacement here is going to be the magnitude of force multiplied by the direct influence coefficient Aii corresponding to location I, and the average force, because the force commenced from 0 and then reached the final magnitude Fi, so the average force is half of Fi. So the total work done becomes half of Fi into Aii into Fi, that is the deflection part. Okay, now once this force has reached the final magnitude Fi, we start applying the force Fj once again, starting gradually. So when this force Fj is being applied at location J, the work done by this force Fj, as we done in the previous case, it is half of Fj because the force is starting from 0 and then reaching the final magnitude Fj in due course of time. This is the average force, and this is multiplied by the deflection under the influence of force Fj, and here the deflection is being given by Ajj, that is a direct influence coefficient corresponding to location J multiplied by the magnitude of this force Fj. So this is the work done by Fj. But when this force Fj is being applied, the beam is getting deflected not only at the location J, but is also undergoing deflection at all other locations including location I. And due to this deflection here, the displacement at location I, this force Fi will do additional work. Now that additional work would be equal to this force Fi, because it is already at its final magnitude. That force Fi multiplied by the deflection at location I under the influence of this force Fj. Now the deflection at I due to force Fj is going to be Fj multiplied by the cross influence coefficient Aij. So this is the deflection or displacement component, and when we multiply this by the force Fi, we get the additional work done by Fi. Now the total work done under this first scheme of loading, the subscript 1 is showing the loading scheme 1. That is, first we apply Fi, then we apply Fj. So the total work done becomes equal to the initial work done by force Fi plus the work done by force Fj plus the additional work done by force Fi when force Fj is applied. So this is the first case of the total work done under loading scheme 1. Now we take up the second scheme where the order of application of Fi and Fj has been reversed. So we first apply Fj and then we'll follow up with the application of Fi. So as we have done before, when we apply Fj, the amount of work done by Fj is the average force, that is half of Fj as explained earlier, multiplied by the location, the displacement at location j, that is Ajj, the direct influence coefficient corresponding to j, multiplied by the force Fj. So this is the work done when force Fj is acting alone. Now in the next step we apply force Fi at location I here. So when this force is applied, it does some work, right? Just the same way as Fj had done in the scheme 1. So the work done by Fi is half of Fi, because the force is beginning from 0 and reaching final. So this is the average force multiplied by the net displacement, and that is Aii into Fi. And as in the last scheme, in this case now force Fj will do additional work, and that is given by the displacement at location j multiplied by the force Fj, which is already acting at its full magnitude. So displacement at j due to unit load at I is supposed to be Aji, and under the influence of force Fi, the displacement at j becomes Fi multiplied by the cross influence coefficient Aji. So this is the net displacement, and this is now multiplied by Fj, and we get this Agi into Fi Fj. So the total work done in the second schema is half Aii Fi square plus half Ajj Fj square plus Aji Fi Fj. Now because the final deflection of this beam, or for that matter the potential energy stored in the beam, in the first scheme and the second loading scheme is going to be same, we just equate the total work done in both the cases. So here is the summary of the proof for Maxwell's theorem. So in the first case we get total work done this much, in the second case we get total work done this much. We just equate these two and cancel out the common terms. So half of Aii Fi square cancels against half of Aii Fi square here. Likewise the second term also gets cancelled. That means the third term, these two terms, they must be equal. We can cancel out Fi and Fj because they are non-zero. So all we are left with is that Aij is equal to Aji. So this is the proof for the Maxwell's theorem, that is the deflection at location I under the influence of a unit load acting at j would be equal to the deflection at location j under the influence of a unit load acting at location I. Thanks.